Hello everyone. In this video I'm going to show you how to solve the homework problem 4. Okay, so in this problem it says an aerial field will be placed on the site and estimates the ultimate consolidation settlement of the site, and then estimate settlement after 6 months, so that's a time rate problem, and estimate the total water pressure at the point A, 2 feet below the sand clay boundary, and then estimate the effective stress at the same point and estimate the time to reach the ultimate settlement. Alright, and let's get started. Okay. Okay, so part A is actually covered in the previous lectures, right? So we're gonna estimate the ultimate settlement for the clay, for the entire clay. So what we are actually looking at is the average settlement for the clay layer. So for part A, we are looking at the settlement at mid depths of the clay, right? Okay, so by doing that, we have to estimate the initial effective stress and the final effective stress at the midpoint, at the mid depths of the clay. Okay, so let's estimate the initial effective stress. Initial effective stress takes place when the field is not placed, right? So before the field is placed on the soil, and we know the groundwater table is at here, so the initial stress would be the total stress minus the pore water pressure. So the total stress is all the stress above the point, right, except the field. So it will be equal to 106 times 6 pound per foot cubed, and times 6 feet, and then plus the second layer, saturated sand, so 124 PCF, and times the thickness 4 feet, and just keep going, and plus 4 feet above the point of the clay, and plus 11A, and times 4 feet. Okay, so that's the total stress, and we have to subtract it. We have to subtract the pore water pressure. So at that point, the pressure head is the distance from that point to the groundwater table, so it's going to be 4 plus 4. So my water pressure going to be 62.4 times the pressure head. That's 8 feet. Okay, and when I calculated, I got 1,105 PSF. Right, and then stress increment at the point would be equal to the stress caused by the field. So delta sigma is equal to 115 times 10. Equals 1150 psf. Okay. And that we can obtain the final stress, right? So the final stress, final effective stress is going to be the initial plus the increment. That equals 2255. Right, so remember the three cases, which equation we're going to use. So typically I like to draw the void ratio and the log effective stress relationship, right? So I like to draw that. So that way I don't need the equation slide. Okay, and it tells us we need the slopes. What it tells us, the slopes. Let's look at the. Oh, it tells us right here. So C sub C, C sub S, 0.05 and 0.42. Okay, so that means the slope as here is 0.05 and the slope of the primary consolidation is 0.42. Okay, and then we need a pre-consolidation, right? So we know OCR is that for us to find it out. Okay, so OCR is defined as pre-consolidation stress to initial stress ratio is equal to 1.5, and we just calculated the initial stress, so that way I'll get the pre-consolidation stress is 1.5 times initial stress. And is equals 1657. Okay, so let me verify it. So 1.5 times 1105. Yeah, so I got 0.5 PSF. Alright, so here I got my pre-consolidation stress 1657.5. And then initial stress is less than pre-consolidation stress, so it's 1105, and the final stress is greater than that. Final stress is 2255. Okay, so that's case 3, right? So that's the case 3. So therefore we're gonna use the case 3 equation, but for me I don't need the equation sheet because it's just a matter of finding your delta E, right? So your delta E and your settlement is H naught over 1 plus E naught times delta E. Okay, so from there I can estimate my ultimate settlement as is equal to H naught over H naught is the original height, so origin thickness, so 8 feet over 1 plus the initial void ratio of 0.9, and then times 0.05 log pre-consolidation stress over initial stress, and plus this part is going to be 0.42 log 2255 over 1657.5, right? And when you calculate it, you will get 0.27 feet, or you can convert it to inches, so 3.2 inches. Okay. Okay. Okay, next let's look at the part B. Part B, let us estimate the settlement after 6 months. So it's a time rate problem. So my first thought would be calculate TV from C sub V, right? Okay, 6 months is about 180 days. Okay. So then part B. Okay, so 6 months, T is 6 months, and C sub V is 0.018. Then let's calculate TV first. So TV is equal to CV times T over HDR squared. Okay, and then C sub V is 0.018 feet squared per day, and then 6 months is 180 days. And divided by HDR, which is the drainage pass. Drainage pass means for this one, so we have sand on the top as well as on the bottom, means it's the two-way drainage, right? So the water gonna drain from the middle, up and down, right? So HDR would be half of the length, so my HDR gonna be 4 feet. Right, so from there I calculate T sub V equals 0.2025, so I'm just gonna round it up to 0.2, just make a lot easier. And then it asks for settlement. Okay, ask for the settlement. All right, so the settlement means must ask for 6 months. The settlement would be a fraction of the total, settlement, right? So like I said in the class, so there are 2 graphs we want to use. Okay, so this graph is going to help us to determine the percent consolidation. So once we enter time factor, we can find the U, right? So if you enter 0.2, it's right here. Okay. And then we can read the corresponding U, right? Yeah, so about 50%. So means 60 months later, 50% of consolidation would be completed. that, read the UTV chart. Read from UTV chart, then enter TV. U is 50%. So that means my settlement at the 6 months would be 50% out of the total, out of the ultimate, right? So say 3.2 inches is the maximum settlement. Then at 6 months, I'm gonna have 1.6 inches settlement at 6 months. Right? Okay. Now let's look at the part C. Estimate the total water pressure 2 feet into the clay. 2 feet into clay, point A, at 6 months. Pore water pressure. Okay. Then, so anything related to pore water pressure, we want to look at the this one. We're gonna look at the ZUZ chart, right? Because consolidation ratio is the function of excess pore water pressure. So if we enter TV and enter Z, we should be able to get the consolidation ratio, right? And then we can calculate the excess pore water pressure from there. Okay, then okay, part C. Since we already know that TV is about 0.2, right? So 0.2, it's just easier. We just take 0.2, and then and we need Z, the depth factor. So the depth factor is the depth over HDR. So it's gonna be 2 feet over 4 feet. So it's gonna be 1.5. So it's gonna be half, 0.5. Then from the chart, we're gonna enter 0.5. So right here, right? So just gonna trace it, and until this one intersect with the 0.2 curve. So about right here. Okay. So enter TV and enter the depth factor Z. We eventually can read my UZ is 0.46. So about 0.46, 0.45. Okay. Okay, so from the UZ chart, I'll get UZ, say 0.45, let's say 0.45. Okay, or if you read 0.46, it's totally okay. Okay. So let's just take 0.46. Okay, and then UZ. So UZ equals 1 minus UEZ, excess pore water pressure at that depth, at the point of interest, over UE nut, right? And we know that UE nut is the initial pore water pressure is equal to the stress increment, so equal to 1150 PSF, right? So it's just equal to the 115 times 10. Okay, so from there I can calculate my UEZ equals UE nut times 1 minus 0.46. Okay. And then equals 621. All right. Okay, so that's the excess pore water pressure. So that is the additional pore water pressure added to point A after the fill is placed, after the fill is put in place. And its original pore water pressure at A would be original pore water pressure at A gonna be the pressure head, right? Pressure head is going to be the distance from A to the groundwater table, so it's going to be 2 plus 6. So initial pore water pressure going to be the water density times 6 feet, right? Equals 561.6 PSF. Okay, and then the total pressure at A gonna be the initial pore water pressure plus the excess pore water pressure. So it's gonna be 1182.6. Okay, and then part D would be pretty straightforward. Part D asks for effective stress at point A, and then what I'm gonna do, actually there are two ways to do it, right? The total stress, right? Okay, so effective stress just refer to the basic definition. So effective stress equals to the total stress minus minus the pore water pressure, right? We just calculated the total pore water pressure, and then, you know, we also calculated the final stress. Okay, we're gonna calculate the total stress at point A. So the total stress at point A equals, so just add everything together. So it's gonna be the fill. So that's gonna be 1150, and then plus the sand 106 times 6, and then plus 124 times 4, and then plus 118 times 2. And that equals 2,518 PSF. Okay. Okay, and then the effective stress just going to be the difference between the total stress and the pore water pressure. So it's going to be 2518 minus this guy, right? So 1182.6 PSF equals 1335.4. Right? Okay. And then what's the last question? So the last question is the estimate the time to reach the ultimate settlement. Okay, so that involves the time estimate. So that involves this chart, right? And typically we assume that when U equals 90% and is regarded as completed. So when U equals 90, right? So we very commonly we said when U equals 90%, then the typical T sub V equals 0.848, right? Okay. So that means part E. So when U equals 90%, and then T sub V equals 0.848, and then T sub V equals CV times T over HDR. So and then we can estimate T equals TV times squared, don't forget the square, HDR squared over C sub V. So it's equal TV 0.848 and then HDR is just 4 feet squared. C sub V is 0.018 feet squared over per day, right? So remember to keep the unit consistent. And there I got about 754 days, and if you divide it by 365 days, so it's approximately about 2.1 years. Alright, and that's it. Alright, I hope this video is helpful, and thank you for watching.